So the question remains, how do you know which algorithm to use in which case? And the truth be told, it really depends, of course, on the number of items or elements that you're actually going to be sorting. Now, of course, we want to answer this question for any type of choices that we're making when we're programmers, whether we're deciding which algorithm to use in which scenario. So we need a way to compare our different algorithms. So there's a number of different comparison tools, but in this class what we're going to do is we're going to focus on something called BigOh notation. And it goes by a few other names such as asymptotic analysis and the complexity of a program. Essentially what we're doing is we're checking to see how many operations or how many steps need to occur in order for the algorithm to complete. And the BigOh notation, it focuses on a worst case scenario. So in the worst case scenario, how many steps is it going to require to complete the task? I wrote a simple little program here that essentially just creates a variable called num and gives it the value 0. And then it has a loop that goes through n times. Now n can be anything, it doesn't really matter. It could be a parameter in a subprogram, but the point is that the loop is going to loop n times, and for each iteration of the loop it's going to do one operation that essentially adds the value of I to num. It doesn't really matter what's going on inside. What matters is how many steps are being taken. So what we can look at is we know that there's one step here to define the variable and give it a value. So we have one here, and then inside of the for loop we have another one. But the thing is, let me just actually put another one here, a 1. But then we also have a certain number of comparisons. Every iteration of the loop, it's comparing to check to see if I is still less than n. Well, the question is, well, how many times is it going to do that? Well, it's going to do it n times. So what we have here is we have a value of 1 plus n comparisons, and for each comparison we have another operation. So we rarely have n times 1. So what we have is 1 plus n. Now the question is, well, what does it matter? So let's think about this in terms of input. Let's say, for example, n is the value 10. What you're going to end up with it for a number of steps is 1 plus 10, which is essentially going to be 11 steps. Let's make a quick little chart here. Now if n is 100, essentially we're going to have 101 steps. If n is 1,000,000, we're going to have 1,000,001 steps. What you can see from this is really as n gets bigger, that extra added 1 is kind of insignificant. So it doesn't really make a difference in here. So if we were to modify this and do something else inside the for loop, let's say, for example, we were just doing, we did num equals num divided by 2 now. Doesn't really make a difference. Essentially, instead of one operation here, we'd have another one. So we'd have 2 times n. Well, if we modified this a little bit, if we did have 2 times n, obviously our values for our steps are going to be a little different. So let's take a look at that. If n is a value of 10, that means that we'd have 2 times 10, which is 20 plus 1, so it's going to give us 21. And then 100, it's going to give us 201. And then 2,000,001. What we come up with is a very similar scenario. First of all, as n increases, again, the 1 is really pretty insignificant, so we can kind of ignore it. We don't really care about it. And again, as n increases, even the multiplicative power, the 2 here, not power, sorry, the multiplicative, it doesn't really make a difference. It's not adding a significant amount, especially as n increases into the millions and billions and billions and billions. So we can actually ignore that as well. So the only real factor here is that n. So the number of steps is directly proportional to the value of n. So the way that we would write this in BigOh notation is we would say that it is BigOh of n. Another way of saying this is that it's linear. meaning as n increases, the problem increases in size proportionally. So if we were to graph it, as n increases, we would see that we would get a nice line. Now, of course, if we come into another algorithm that, say, for example, well, let's look at I'll just quickly delete all this stuff. Let's think about the scenario of the bubble sort. The bubble sort, if you recall, essentially has a few numbers, and let's just write down some numbers here and see if I can remember what they were. -7, -3, 5, 4, and 3. Essentially what it does is it looks at each number and it compares it against each one until it gets up to the end. And again, and then it starts over again and it repeats the process. And then again, and it continues to do this. Essentially what you end up with is you end up with an outer loop that goes n times. And then an inner loop that goes at really n minus I times. Now, just like we showed before, the multiplicative here of this I is kind of irrelevant. So we know we have n times we have n comparisons or n steps for the outer loop, and so we're going to multiply this because for every outer loop we do the entire inner loop completely. So it's going to be a multiplication. So we're going to have really n times n minus I. Now, since this, again, this minus I is just like our 1 plus whatever, or 1 plus n, it's negligible. So we can get rid of that. So what we actually end up with is n times n, or n squared. So that means that our bubble sort has a notation of BigOh of n squared. Again, if we were to graph something like that, instead of a linear BigOh of n, which looks like this, we end up with something a little bit more painful. As n increases, the steps it requires increase a lot more. So if we were to do another chart, let's quickly, I should just scroll down so we can make space a little bit lower here. If we were to do another chart and we have n and then steps, we know that the function is n squared, BigOh of n squared. If n is 10, the number of steps is 100. If n is 100, then we have 100 times 100. So we end up with 10,000. So as the number increases, we end up with n squared. You can see that it greatly increases really, really fast. Another form of algorithm we talked about was the merge sort. And the merge sort's a very interesting one because it does something that none of these algorithms does. Like neither the binary or sorry, not the binary, the bubble or the insertion, or even that little algorithm that I was showing you 2 seconds ago with the for loop. The merge sort does a division. So it takes our list of items and it divides it in half. And then it divides it in half again and again and again and again. And then it starts to merge things. So it kind of finds this halfway point, roughly speaking. Oops, that didn't work out too well over here. And then it merges, and then it merges these, and then it merges, sorry, not those ones, and then it merges these ones. And then it merges these ones until we end up with another final result. So what actually happened here is what we have is we have this division by 2 until we get down to our actual base cases. And just to save a huge mathematical discussion, what we can say is that takes log n time. And then the merge itself, if you remember the algorithm, it essentially said, look at each element, say which one is larger. Look at each element, which one is larger again. And so on, or sorry, smaller, and then smaller, and then smaller, and smaller. So we're always trying to find the smallest element, putting on the left-hand side of the merged array. So what that means is we have to look at every single element. Well, how many times do we have to look at every single element? Well, we really only have to look at it once because we're always taking the next lowest item. So what we have here is n. So since this is a grouped item, what we end up with is log n times n. So what's the final asymptotic analysis for this, or BigOh notation? It's actually BigOh of n for the merge times log n for the division. This is log base 2, in case you were wondering. Now, this is actually pretty safe. So in a lot of cases when you're doing recursion or a lot of different algorithms, you're going to find that there's that division by 2 to split up the problem by half, and then by half, by half, by half. For our purposes, you can always assume that that is going to require log base 2 of n to do that operation. In the merge's case, the building back up of the whole thing takes n times, because we have to look at each element once to do that. So in order to do this, we're going to multiply these two things together, so we end up with BigOh of n log n. So to look at the complexity or asymptotic analysis or the BigOh notation of merge sort, we know that it's BigOh of n log n now. So how does that actually break down into the steps? How many steps is that? Well, let's take a look at it for a second. We know if it was just BigOh of n, it'd be whatever the equivalent value of n is. So n for 10 would give us 10 steps, n for 1,000 would give us 1,000 steps, and so on and so forth. But this is n times log n. Hopefully it won't add a huge amount, but it definitely will add some. So for example, if we had 10 steps, the log of n is going to be about 3.3. So then we have to take that 3.3 and multiply it by n. What we end up with then is approximately 33 steps for 10 items. Now for 1,000 items, that's a little bit different. What we end up with is a log of about 9.9 approximately. So we multiply that by 10, we end up with 99 steps. Now let's look at a million. A million, much bigger number. And what we end up with for the log is about 19.9. We multiply that by 10 now again. Sorry, we need to back up a step. This was 9.9. It would actually be quite a few more, not 99. It would actually be multiplying it by 1,000, not 10. So we end up with 9,900. And for a million, if we end up with 19.9, we have to multiply that by 1,000, or multiply that by a million. And what we end up with is 19.9 times 19.9 million, actually, which makes sense. So we have 19,900,000. So obviously that number escalates quite a bit. So if this was just linear time, we'd only be looking at a million comparisons or a million operations as opposed to almost 20 million operations. So it does make a difference. It's that log n factor that's being multiplied by the n to get this value.